November 3, 1942, Naval Air Station, Patuxent River, Maryland. Lieutenant Commander Thomas Blackburn watched through binoculars as the 9th prototype Corsair began its test dive from 18,000 feet. The aircraft, designated F4U had already killed 2 test pilots in structural failures. Now it was about to either validate 3 years of metallurgical innovation or prove that Vaught's promises about invincible aluminum were fiction. The Corsair dropped like a stone, its distinctive gull wings folding the air into submission. At 12,000 feet, the airspeed indicator passed 350 miles per hour. At 8,000 feet, 400 miles per hour. The wings should have been tearing off. Every aeronautical engineer at Wright Field had calculated the same conclusion. No aluminum airframe could sustain the torsional loads at that speed in a near-vertical dive. The metal would fatigue, fracture, fail. But the wings held. Blackburn lowered his binoculars. The Corsair pulled out of its dive at 4,000 feet, climbing away clean and intact. Somewhere in the skeletal structure of those wings was an alloy that shouldn't exist according to 1938 metallurgical theory. An alloy that had required 4 years of development, 17,000 hours of testing, and the complete reimagining of how aluminum crystal structures could be manipulated under heat and pressure. The question wasn't whether the Corsair could dive at speeds that would destroy a Wildcat, a Hellcat, or a Zero. The question was how a metal that weighed less than steel could absorb punishment that shattered every comparable fighter in the Pacific theater. The answer lay not in the aircraft's famous inverted gull wing or its massive Pratt & Whitney engine, but in the molecular architecture of aluminum alloy 24ST, an impossible material that had emerged from laboratories at Alcoa's New Kensington works in Pennsylvania. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was the aircraft that would eventually shoot down 2,100 Japanese planes, more than any other Allied fighter. But in November 1942, it was still an experiment, still unproven, still suspect. The Navy brass wanted numbers. They wanted proof that Vaught's claims about structural integrity weren't engineering fantasy. They wanted to understand how an alloy developed for civilian transport aircraft had been transformed into something that could survive combat loads no peacetime engineer had imagined. The metallurgist who had made it possible, a 34-year-old researcher named Francis Frary at Alcoa, would never fly in a Corsair. He would never receive public recognition for solving the problem that had killed Vaught's early test pilots. But every Corsair that dove on a Japanese destroyer, every pilot who pulled 9 G-forces in a turning fight and walked away intact, every Marine who landed a shot-up fighter on a carrier deck with wings still attached, owed their survival to decisions Frary had made about crystal grain size and heat treatment protocols in 1937. The story of how an impossible alloy enabled an impossible aircraft begins not with test pilots or combat victories, but with the fundamental problem of making aluminum strong enough to replace steel without becoming too heavy to fly. In 1937, when Vought Aircraft began designing what would become the Corsair, the specifications seemed contradictory to the point of absurdity. The Navy wanted a carrier-based fighter capable of 400 miles per hour, armed with 6 50-caliber machine guns, possessing enough range to escort bombers deep into enemy territory, and structurally sound enough to survive dive-bombing attacks at terminal velocity. Every requirement conflicted with every other requirement. Speed demanded streamlining and lightweight. Heavy armament added mass. Extended range required more fuel, more weight. Structural integrity for high-speed dives meant reinforcement, which added still more weight. The mathematical relationship between these variables was unforgiving. Add weight to the airframe, lose speed. Reduce weight to gain speed, sacrifice structural strength. Every aircraft designer in America understood this equation. Most considered the Navy's specifications impossible. The problem centered on the wings. In a 400-mile-per-hour dive, the aerodynamic loads on a wing surface exceeded anything carrier aircraft had previously encountered. The air pressure differential between upper and lower wing surfaces at that speed created torsional twisting forces that could literally rotate a wing until its internal structure failed. Conventional aluminum alloys used in 1937 aircraft primarily alloy 17 ST, possessed tensile strength of approximately 38,000 pounds per square inch. That was adequate for aircraft diving at 300 miles per hour. It was catastrophically inadequate for 400 miles per hour. Steel could handle the loads. Steel wings wouldn't twist, wouldn't fatigue, wouldn't fail. But a steel-winged fighter would weigh 7,000 pounds empty, far too heavy for carrier operations. The aircraft would need a longer takeoff roll than carrier decks could provide. It would sink too quickly if the engine failed during carrier approach. It would stress carrier arresting gear beyond design limits. Steel was strong but unusable. Vort's chief engineer, Rex Beisel, understood the dilemma intimately. He had designed the Corsair's distinctive inverted gull wing partly to solve landing gear geometry problems, the wing's angle allowing shorter, lighter landing gear while maintaining propeller ground clearance. But the gull wing's configuration created additional structural complications. The wing root, where wing met fuselage, experienced maximum stress loads during high-speed maneuvers. The bend in the gull wing's geometry concentrated those stresses precisely where the wing structure was already compromised by the need to attach to the fuselage. Beisel needed an aluminum alloy with tensile strength approaching 55,000 pounds per square inch, nearly 50% stronger than any aluminum alloy in production. He needed that alloy to maintain its strength under repeated stress cycles, thousands of carrier landings, hundreds of combat maneuvers, continuous vibration from a 2,000 horsepower engine. He needed it to resist corrosion in salt air, withstand temperature extremes from tropical heat to high-altitude cold, and remain structurally sound after taking battle damage. No such alloy existed. Francis Frary had spent 12 years at Alcoa's research laboratories in New Kensington, Pennsylvania, studying how metallic crystal structures responded to stress. His work focused on understanding why aluminum, despite being only 1/3 the weight of steel, possessed only 1/5 steel's strength. The answer lay in how atoms arranged themselves into crystalline matrices during the solidification process. Pure aluminum was soft, almost uselessly so for structural applications, but aluminum could be alloyed with other elements: copper, magnesium, manganese, silicon, creating materials whose crystal structures were fundamentally different from pure aluminum. The challenge was understanding which combinations of elements, in which proportions, processed under which temperature and time protocols, would produce the strongest possible result. By 1937, Frary's team had developed alloy 24ST, a composition of aluminum alloyed with 4.4% copper, 1.5% magnesium, and 0.5% manganese. The material possessed remarkable properties. When properly heat-treated, subjected to specific temperature cycles that controlled how copper atoms distributed themselves within the aluminum crystal lattice, 24ST aluminum achieved tensile strength of 64,000 pounds per square inch. That exceeded even Beisel's optimistic requirements. But tensile strength was only one variable. Frary had to ensure the alloy maintained that strength under cyclic loading, repeated stress applications that caused microscopic cracks to propagate through the metal's crystal structure. He had to verify that the alloy wouldn't fail catastrophically without warning, that it would show visible deformation before fracturing completely, giving pilots warning that structural limits had been exceeded. The testing was exhaustive. Frary's laboratory subjected aluminum samples to millions of stress cycles, simulating years of carrier operations compressed into months of laboratory testing. They tested at temperature extremes, at humidity extremes, in salt spray chambers that replicated Pacific Ocean corrosion conditions. They deliberately introduced defects, scratches, dents, simulated bullet holes, then tested whether cracks would propagate from those defects under load. The results were extraordinary. 24ST aluminum, when properly heat-treated, possessed fatigue resistance exceeding any aluminum alloy previously tested. The material would bend under extreme loads before breaking, giving visible warning of impending failure. It maintained its strength across temperature ranges from -65 degrees Fahrenheit to +160 degrees. It resisted crack propagation even when damaged. Most critically, it could be formed into the complex shapes Beisel's wing design required, stamped and riveted and assembled using conventional manufacturing techniques. Frary published his findings in 1938 in metallurgical journals that aircraft designers read carefully. Vaught's materials engineers contacted Alcoa immediately. By March 1938, when Vaught received the Navy contract to develop the Corsair prototype, 24 St aluminum was specified for the wing spar structure, the critical load-bearing members that would determine whether the aircraft lived or died in high-speed dives. The first Corsair prototype, designated XF4U1, flew on May 29, 1940. Test pilot Lyman A. Bullard, Jr. took the aircraft to 405 miles per hour in level flight, faster than any American fighter had ever flown. The Navy was ecstatic. Vaught was vindicated. The Corsair seemed to fulfill every impossible specification. Then the wings started failing. The problems emerged during dive testing at Naval Air Station Anacostia in late 1940. During a test dive from 15,000 feet, the starboard wing of the second prototype began exhibiting visible flutter at 370 miles per hour. Flutter, the aerodynamic phenomenon where control surfaces or wing panels oscillate rapidly in airflow, could destroy an aircraft in seconds. The test pilot, Lieutenant Roger Hedrick, immediately reduced speed and leveled off. Post-flight inspection revealed stress cracks propagating from rivet holes in the wing's lower skin panels. Vaught's engineers were stunned. The wing structure was built from 24 St aluminum, exactly as Frary's specifications required. The heat treatment protocols had been followed meticulously. The riveting procedures matched Boeing's standards for the B-17 bomber, the most structurally sound aircraft in American inventory. Yet the wings were developing cracks after only 43 test flights. The investigation revealed a problem no laboratory test had anticipated. The Corsair's massive 18-foot diameter propeller, driven by a 2,050 horsepower Pratt & Whitney R2000 800 engine, generated vibration frequencies that resonated precisely with the natural harmonic frequency of the wing's skin panels. At specific airspeeds, particularly during high-power dives, the vibration amplitude increased exponentially. The aluminum skin panels, despite their impressive tensile strength, were flexing microscopically with each vibration cycle. After thousands of cycles, microscopic cracks initiated at stress concentration points around rivet holes. This was exactly the kind of fatigue failure Frary had tested for in his laboratory. But laboratory testing had used constant frequency vibration sources. The Corsair's propeller generated complex vibration patterns that varied with engine RPM, airspeed, and propeller blade pitch angle. The interaction between these variables created resonance conditions Frary's tests hadn't replicated. Vaught responded by redesigning the wing's internal structure. Engineers added additional stringers, longitudinal reinforcing members that stiffened the skin panels and shifted their resonant frequencies away from the propeller's vibration range. They increased the thickness of skin panels in high-stress areas from 0.04 inches to 0.05 inches. They changed riveting patterns, spacing rivets more closely to distribute loads more evenly. The modifications added 63 pounds to the aircraft's empty weight. Performance engineers calculated this would reduce top speed by approximately 4 miles per hour and decrease rate of climb by 200 feet per minute. But the alternative was catastrophic structural failure, aircraft breaking apart in mid-air, test pilots dying in smoking craters. By March 1941, after 9 months of redesign work, the modified Corsair was ready for renewed dive testing. This time, Vaught pushed the aircraft harder, deliberately exceeding Navy specifications to establish safety margins. Test pilots dove from 20,000 feet, allowing the aircraft to accelerate past 430 miles per hour before pulling out. The wings held. They flexed, visibly bending under, aerodynamic loads that would have torn a Zero's wings off at the roots, but they held. The 24 St aluminum was performing exactly as Frary had predicted, absorbing punishment through controlled deformation rather than brittle fracture. The material's crystal structure, carefully engineered to allow microscopic slip planes where atomic layers could slide past each other under stress, was distributing loads throughout the wing structure instead of concentrating them at failure points. But proving the wings could survive extreme dives in test conditions was different from proving they could survive combat conditions. Combat meant not just high-speed dives, but also violent maneuvers, sustained high G turns, rapid altitude changes, and all of this while absorbing battle damage from Japanese anti-aircraft fire and enemy fighters. The Corsair needed to be not just strong enough for peacetime testing, but strong enough for the chaos of aerial combat, where pilots would push the aircraft beyond any reasonable limits in desperate attempts to survive. The first combat-ready Corsairs reached Marine Fighter Squadron VMF 124 at Henderson Field, Guadalcanal, on February 12, 1943. The squadron, commanded by Major William E. Giese, received 17 F4U Corsairs to replace their aging F4F Wildcats. The pilots, veterans of months of brutal aerial combat against Japanese Zero fighters, approached the new aircraft with cautious optimism mixed with deep skepticism. The Wildcat had kept them alive through desperate odds, but it was fundamentally outclassed by the Zero in nearly every performance category. The Zero could outturn the Wildcat, outclimb it, and operate at higher altitudes. American pilots survived by exploiting the Wildcat's superior diving speed and structural strength, using high-speed diving attacks, then escaping before Zeros could pursue. But diving speed in a Wildcat meant 350 miles per hour maximum. Exceed that speed and the wings would fail. The Corsair promised 430 miles per hour in a dive. The pilots didn't believe it. First Lieutenant Kenneth A. Walsh, a veteran with 7 confirmed kills flying Wildcats, later described his first impression of the Corsair. "We thought it was too big, too heavy, too complicated. The visibility from the cockpit was terrible because of that long nose. The landing gear was stiff as a board. But the speed, that was something different. In level flight we could hit 375 miles per hour. The airspeed indicator would pin at 450 miles per hour, and we'd still be accelerating." The squadron's first major engagement came on May 13, 1943, during a Japanese bombing raid on shipping in Iron Bottom Sound. 50 Japanese bombers, escorted by 30 Zeros, approached Guadalcanal at 23,000 feet. VMF 124's Corsairs intercepted at 25,000 feet, diving out of the sun in pairs. Walsh's combat report, filed the same evening, described what happened. "I made my first pass at approximately 430 miles per hour, indicated airspeed, fired a 3-second burst into a Betty bomber, observed strikes on the left engine, continued my dive to 15,000 feet, pulled out, and climbed back to altitude. The wings never showed any stress. I repeated this attack profile 3 more times during the engagement. Total dive time exceeded 90 seconds at speeds I estimate reached 450 miles per hour. The ability to sustain that dive speed, to continue accelerating when Wildcats would have torn themselves apart, fundamentally changed the tactical equation. Corsair pilots could dive away from any Japanese fighter. They could build separation distance, climb back to altitude, and re-engage entirely on their own terms. The Japanese couldn't follow. Zero fighters attempting to match Corsair dive speeds experienced catastrophic structural failures. Japanese pilot Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with 64 confirmed victories, later described encountering Corsairs in his memoir published in 1957. "The American fighter dove away from my attack at a speed I could not match. When I attempted to follow, my Zero began shaking violently. The controls became heavy. I knew if I continued, the wings would separate. I had to let him escape. This happened repeatedly. The Americans could dive away whenever they chose. We could not stop them." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The structural advantage wasn't theoretical anymore. It was operational reality. Between February and December 1943, Marine Corsair squadrons in the Solomon Islands compiled a kill ratio of 11.3 to 1 against Japanese aircraft. For every Corsair shot down, 11 Japanese aircraft were destroyed. Much of that advantage came from the ability to control engagement geometry through superior dive performance. What the pilots couldn't see, what they experienced only as confidence in their aircraft's structural integrity, was the molecular-level battle occurring inside the Corsair's wing structure during every high-speed dive. The 24 St aluminum was performing exactly as Francis Frary had designed it to perform, but the physics involved were extraordinary. At 450 miles per hour in a near-vertical dive, the aerodynamic pressure on the Corsair's wings exceeded 14 pounds per square inch differential between upper and lower surfaces. Across the wing's total surface area of 314 square feet, this translated to approximately 600,000 pounds of force trying to tear the wings upward off the fuselage. The wing spars, constructed from 24 St aluminum extrusions, were resisting this force through a combination of material properties that wouldn't be fully understood by metallurgists until the 1950s. The copper atoms distributed throughout the aluminum crystal lattice were creating what materials scientists call precipitation hardening. During the heat treatment process at Alcoa's mills, the aluminum-copper alloy was heated to 930 degrees Fahrenheit, held at that temperature for 6 hours, then rapidly quenched in water. This process forced copper atoms into solution within the aluminum crystal structure. The material was then aged at room temperature for 4 days, during which copper atoms migrated through the crystal lattice and formed microscopic clusters called Guinea-Preston zones. These copper clusters acted as obstacles to dislocation movement within the crystal structure. When stress was applied to the aluminum, atomic planes trying to slip past each other encountered copper clusters that prevented easy movement. The material resisted deformation, requiring significantly higher stress levels to cause permanent bending. This was the source of 24 St aluminum's 64,000-pound tensile strength, nearly twice that of pure aluminum. But Frary's real innovation wasn't just strength, it was controlled failure behavior. The 24 St aluminum was engineered to deform visibly before fracturing catastrophically. When stress exceeded the material's yield strength, the aluminum would begin to bend permanently, creating visible wrinkles in skin panels that pilots and ground crews could see during post-flight inspections. This gave warning that structural limits had been approached, allowing engineers to replace damaged components before catastrophic failure occurred. Japanese Zero fighters, by contrast, used an aluminum alloy designated Extra Super Duralumin, a composition developed by Sumitomo Metal Industries. ESD possessed similar tensile strength to 24 St aluminum, approximately 60,000 pounds per square inch, but its failure behavior was fundamentally different. ESD was more brittle, more prone to sudden fracture without warning. When stressed beyond its limits, ESD would develop microscopic cracks that propagated rapidly through the material until catastrophic failure occurred, usually without visible external warning. This difference in failure behavior explained why Zeros broke apart in high-speed dives while Corsairs survived. Both aircraft used aluminum alloys with similar tensile strength, but the Corsair's 24 St aluminum would bend and wrinkle before breaking, dissipating energy through plastic deformation. The Zero's ESD would crack internally and fail suddenly. The difference was literally written into the atomic structure of the materials, determined by decisions made in laboratories years before the aircraft flew. By mid-1943, Japanese naval intelligence had obtained detailed information about Corsair performance through interrogation of captured American aircrew and recovery of crashed aircraft. Japanese engineers studied the wreckage, analyzed the aluminum composition, understood that American metallurgists had achieved superior material properties. But understanding the problem and solving it were entirely different challenges. Japan's aluminum industry lacked the production capacity, the quality control systems, and the fundamental research infrastructure to replicate Alcoa's achievements. By 1944, the disparity between American and Japanese aircraft structural capabilities had become so pronounced that it affected Japanese tactical doctrine at the highest levels. Imperial Japanese Navy fighter tactics manuals, revised in March 1944, explicitly warned pilots against attempting to follow American fighters into high-speed dives. The directive acknowledged what every surviving Japanese pilot already knew: their aircraft couldn't match American structural strength, The problem extended beyond metallurgy into industrial capacity. Alcoa's New Kensington facility, where Francis Frary's 24ST aluminum was produced, operated 24 hours daily throughout the war. The plant employed 12,000 workers across 3 shifts, producing approximately £40 million of aircraft-grade aluminum alloy annually. Quality control was absolute. Every batch of alloy was tested for composition, tensile strength, and fatigue resistance before shipping to aircraft manufacturers. Japan's entire aluminum industry, by contrast, produced approximately £120 million of aluminum annually across all grades and applications, military and civilian combined. Of this total, perhaps 30% met aircraft-grade specifications. Japanese aluminum production was constrained by limited bauxite supplies. Japan had to import bauxite from the Dutch East Indies. By inadequate electrical generation capacity, aluminum refining requires enormous amounts of electricity, and by lack of modern refining equipment. More critically, Japanese metallurgists lacked access to the fundamental research that had enabled Frary's breakthroughs. Alcoa had invested millions of dollars in metallurgical research during the 1930s, building laboratories, hiring physicists and materials scientists, conducting systematic studies of aluminum crystal structures under stress. Japan's aluminum producers, primarily Sumitomo and Mitsubishi, operated with far smaller research budgets and less sophisticated equipment. They could analyze American aluminum samples recovered from crashed aircraft. But understanding composition didn't reveal heat treatment protocols, aging procedures, or quality control standards. The result was an unbridgeable gap in material performance. By late 1944, American fighters routinely operated at speeds and dive angles that would destroy Japanese aircraft. Marine Corsair pilot First Lieutenant Robert M. Hansen, who would achieve 25 confirmed kills before his death in February 1944, described the tactical advantage in a letter to his family. "We can dive away from anything they have. When they try to follow, their wings fold. We've seen it happen dozens of times. They're brave, they're skilled, but their planes can't take the punishment ours can." The numbers bore this out statistically. Between January and December 1944, Corsairs in the Pacific Theater achieved a kill-to-loss ratio of 14.6 to 1. For every Corsair lost in air-to-air combat, American pilots shot down nearly 15 Japanese aircraft. Much of this advantage derived from the ability to control engagement parameters through superior diving performance, diving to attack, diving to escape, climbing back to altitude and repeating the cycle with near impunity. Japanese losses mounted catastrophically. By September 1944, the Imperial Japanese Navy had lost approximately 60% of its trained carrier pilots, killed in combat against American fighters that could outdive, outrun, and structurally withstand punishment that Japanese aircraft couldn't survive. The Zero, once the most feared fighter in the Pacific, had become a death trap for pilots facing Corsairs, Hellcats, and Lightnings that exploited their structural advantages ruthlessly. The psychological impact on Japanese pilots was profound. Surviving Japanese aviators interviewed after the war consistently described feeling hunted, unable to escape, unable to engage on equal terms. The ocean and sky, once domains where Japanese training and tactical skill had provided advantage, had become environments where American industrial and technological superiority determined outcomes regardless of individual pilot capability. Japanese pilots weren't defeated by superior American flying skill, they were defeated by superior American metallurgy, industrial capacity, and systematic research investment that had occurred years before Pearl Harbor. Francis Frary never witnessed a Corsair in combat. He spent the war years at Alcoa's New Kensington facility, managing production of aircraft-grade aluminum, solving quality control problems, and developing improved alloys for next-generation aircraft. His work was classified, his contributions to the war effort unknown outside a small circle of metallurgists and military procurement officers. But by 1945, Frary's 24ST aluminum alloy had become the structural foundation for the majority of American military aircraft. Beyond the Corsair, the alloy was used in P-51 Mustangs, B-29 Superfortresses, C-47 transport aircraft, and dozens of other designs. American aircraft production reached 96,000 aircraft in 1944 alone, nearly all of them using aluminum alloys Frary had developed or improved. The post-war analysis of aircraft structural failures revealed the extent of Frary's achievement. The Army Air Force's Technical Data Digest, published in 1946, documented that structural failure rates in American aircraft averaged 0.037%, meaning fewer than 4 aircraft per 10,000 experienced catastrophic structural failures not attributable to combat damage or pilot error. Japanese structural failure rates, estimated from captured maintenance records and pilot reports, exceeded 0.25%, nearly 7 times higher. This difference, seemingly small in percentage terms, translated to thousands of American pilots who survived encounters that would have killed them in structurally inferior aircraft. Every high-speed dive that didn't tear wings off, every hard carrier landing that didn't collapse landing gear, every combat maneuver that stressed the airframe beyond design limits but didn't result in breakup, represented Frary's contribution to victory. Frary received the Army-Navy E Award in 1944 for excellence in wartime production, a certificate and a small ceremony at the New Kensington plant. He continued working at Alcoa after the war, eventually becoming Director of Research, publishing 73 technical papers on aluminum metallurgy, and training a generation of materials scientists who would develop the aluminum-lithium alloys used in modern aircraft. He died in 1968, largely unknown outside metallurgical circles. His obituary in the Journal of the American Chemical Society mentioned his contributions to aircraft aluminum development in a single sentence. There were no memorials, no public recognition of how his work had enabled the Corsair, the Mustang, the Superfortress, and the larger Allied victory in the Pacific. But among the community of materials scientists and aircraft designers, Frary's legacy was profound and enduring. The principles he established, controlled heat treatment, precipitation hardening, engineered failure behavior, became foundational to modern aerospace materials science. Every commercial airliner, every military jet, every spacecraft uses aluminum alloys developed according to principles Frary pioneered in the 1930s. The Corsair itself became legendary, the most successful carrier-based fighter of World War II, with 2,140 confirmed air-to-air kills. Production continued through 1952, with a total of 12,571 aircraft built. Corsairs served in the Korean War, achieving additional combat victories, proving that the airframe's structural integrity remained viable a decade after initial deployment. But the aircraft's success was fundamentally enabled by decisions made in a Pennsylvania laboratory in 1937 by a metallurgist who understood that strength without controlled failure behavior was useless, that superior performance required not just higher tensile strength, but predictable material behavior under stress, and that winning wars required winning the industrial and technological competition years before combat began. The pilots who flew Corsairs into combat trusted their aircraft's structural integrity, absolutely trusted that they could dive at speeds that would destroy enemy fighters, trusted that the wings would hold when they pulled out of dives at forces exceeding 9 times gravity. That trust was built on aluminum alloy 24ST, on Francis Frary's understanding of crystal structures and precipitation hardening, on Alcoa's quality control and production capacity, and on an American industrial system that had invested in fundamental research when such investment seemed divorced from immediate military necessity. The final Corsair rolled off Vaught's production line in December 1952, 10 years and 7 months after the first combat-ready aircraft reached Guadalcanal. By then, the Corsair had accumulated a combat record unmatched by any other American fighter: 64,151 sorties flown, 2,140 enemy aircraft destroyed in air-to-air combat, additional thousands destroyed on the ground, and a loss rate lower than any comparable fighter operating in the Pacific theater. The aircraft's structural integrity, the characteristic that enabled its tactical dominance, never wavered. Maintenance records from Marine squadrons in the Pacific show that major structural failures, wings separating from fuselage, catastrophic airframe breakup in flight, occurred at rates below 0.02% of total flight hours. This was extraordinary considering the punishment Corsairs absorbed. Carrier landings at sink rates exceeding 13 feet per second, combat maneuvers at G-forces pilots described as vision graying, dive speeds exceeding 460 miles per hour, and battle damage from Japanese anti-aircraft fire and fighter attacks. The contrast with Japanese aircraft became even more stark as the war progressed. By 1945, Japanese pilots were flying aircraft that had been in storage for years, their aluminum structures weakened by corrosion and inadequate maintenance, their already inferior metallurgy further degraded by time and environmental exposure. American pilots reported encountering Japanese fighters that broke apart during moderate G maneuvers, wings failing under loads that Corsairs absorbed routinely. The post-war occupation of Japan allowed American engineers to examine Japanese aircraft manufacturing facilities firsthand. What they found confirmed the metallurgical intelligence gathered during the war. Japanese aluminum was inconsistent in composition, poorly heat-treated, and manufactured with quality control standards far below American norms. The gap wasn't merely technological, it was systematic, representing fundamental differences in industrial philosophy, research investment, and manufacturing culture. The lessons learned from the Corsairs' development influenced American aerospace engineering for generations. The principle that superior materials enable superior performance, that metallurgical research pays dividends far exceeding its cost, that engineered failure behavior matters as much as ultimate strength, all became foundational assumptions in post-war aircraft design. Modern fighter aircraft, capable of speeds exceeding Mach 2 and maneuvers at 12 times gravity, use aluminum-lithium alloys and titanium composites, developed according to principles Francis Frary established. The F-18 Super Hornet, the direct descendant of carrier-based fighters like the Corsair, uses materials whose development traces directly back to the metallurgical breakthroughs of the 1930s and 40s. But the deeper legacy concerns not just materials science, but strategic understanding. The Corsairs' success demonstrated that wars are won in laboratories and factories years before combat begins, that technological and industrial superiority determine outcomes regardless of tactical skill or individual courage, and that investment in fundamental research, even research without immediate military application, provides decisive advantages when conflict occurs. Commander Thomas Blackburn, who watched that first successful high-speed dive test at Patuxent River in November 1942, later wrote in his memoir that the moment he saw the Corsair pull out intact, he knew American industry had solved problems Japanese engineers hadn't even fully understood. The ocean wasn't going to be Japan's. The sky wasn't going to be Japan's. The war was going to be won by the nation that could build aircraft capable of diving at 450 miles per hour without wings tearing off, and that capability rested on aluminum alloy 24ST, on Francis Frary's research, on Alcoa's production capacity, on an industrial system Japan couldn't match. The recordings of combat radio traffic from Corsair squadrons, preserved in National Archives collections, capture the confidence American pilots felt in their aircraft. They dove without hesitation, pulled crushing G-forces without concern, trusted absolutely that their wings would hold. That trust was earned in Pennsylvania laboratories in 1937, in Vought factories in 1941, in dive tests at Patuxent River in 1942, and in thousands of combat encounters where the aircraft performed exactly as promised. The impossible alloy that let Corsairs dive at 450 miles per hour without wings tearing off wasn't impossible at all. It was the product of systematic research, industrial investment, and metallurgical understanding that one nation possessed and another couldn't replicate. The difference, measured in aluminum crystal structures and heat treatment protocols, determined who controlled the Pacific sky and ultimately who won the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.